When we're thinking about redox reactions, what's the driving force for a redox reaction? So, if we look at this one. This is a single replacement redox reaction. If we look at this, what are the potential products here that would form? Yeah. ZnCl2, and not copper 2 plus.
Oh, sorry.
Copper solid. And so basically we look, are we going from stronger to weaker? So over here, if you look, chloride is a spectator, nothing's changed. So copper 2 plus is what we call our oxidizer. Zn, this will be a reducer. Over here on the product side, we're going to have Zn2 plus, which will be our oxidizer, and copper, which will be our reducer. And then we just look at the chart. The chart says this is stronger, this is weaker, this is weaker here. And so if we're going from stronger is more reactive, less stable. The weaker, which is less reactive, more stable. And so, we expect this to be exothermic. But when we predict reactions, delta H should be negative. That is, we should be dropping down in energy, going from initial to... This would be an energy or enthalpy diagram here. What's the difference between an enthalpy diagram like this and a reaction coordinate diagram? You heard of a reaction coordinate diagram?
No.
A reaction coordinate diagram is involved with kinetics. Thermodynamics tells you if there's a driving force, but, does it give us any information about how long it's going to take for this reaction to occur? I mean, when we look at this delta H, normally if the delta H is very large and very negative, then you expect a pretty energetic reaction, and energetic reactions like that are typically fast. But we don't know because we don't know what the activation barrier is, the activation energy. And so, in thermodynamics, we're most interested in state functions. State functions, all we care about is the initial state and the final state, right? But in kinetics, we want to know what's happening between the two states. That is there a pretty big activation energy? If there's a pretty big activation energy, it might actually be metastable, which is a blend of kinetics and thermodynamics. So kinetics and thermodynamics are two separate topics, but they're related, in that way. And they talk about two different things. One talks about driving force for reaction. Is it a spontaneous reaction? Does it have driving force? Or is it a non-spontaneous reaction? It has no driving force at all. But the kinetics part, we would be looking at, the speed. There are some reactions which do have a driving force, but just don't happen because but not energetic enough.
They can't get over the activation energy.
Right, because even though this looks like a downhill process, there's the hump in order to make this transition state, right, which could slow things down. All right, now we're back to strictly thermodynamics. I don't care how long this is going to take. We just want to know, okay, is there a driving force or not? And you would say that there is a driving force based on energy, right? What about an entropy? So if you look at the entropy changes here, do you see anything really significant? So the entropy looks, the entropy of the reactants versus the entropy of the products doesn't look like there's a significant difference there. And so I'd say this reaction should occur. But normally when we look at reactions, and this is what we haven't been doing, we haven't been looking at entropy, have we? We've only been looking at energy, you know, that is going from less stable to more stable. Well, it turns out that energy is actually related, you know, to entropy as well. Because did you know different forms of energy will have different entropies? You know, so for example, this is an exothermic reaction. So this will be a little bit more review of Chem 1A. Okay, but I'm going to. Well, actually, let's just use. Maybe we should do internal energy. Well, anyway, we have the initial enthalpy and we have the final enthalpy. I didn't do this in Chem 1A because I try to keep it simpler, but we'll just go ahead and do this. The initial enthalpy is equal to what? This is absolute enthalpy. Tell me what the absolute enthalpy equals. I'm sorry? Well, we're talking about the absolute. Okay, what is the energy of a beaker of just copper 2 chloride and zinc sitting in there?
0.
No, it's not 0. There's energy there. What is the energy of that? Well, actually, to speed things along, I'm going to just tell you. It's going to be the internal energy plus PV. P is a constant, so I'm not going to put P initial because P is not going to change because this is enthalpy. Enthalpy, P can't change, right? Due to constant pressure. But V can change. What is the absolute internal energy equal to? Yeah, potential energy initial plus kinetic energy initial, good, plus PV initial. Okay, then over here we have H final, which is going to equal the internal energy final plus PV final, which is going to equal the potential energy final plus the kinetic energy final plus PV final. All right, what's the temperature of the reactants? This is an exothermic reaction. What's the temperature of the reactants we start off with? What do you think? Well, room temperature makes sense. You don't want to heat it up. It's a hassle. Or cool it down. Just do it at room temperature. It's exothermic, so what is the temperature of the products? What will be the temperature of the products? This is exothermic, so it should warm up, correct? And so what will the temperature of the products be? Somebody tell me. Zach, you got it? It's going to be at 25. Well, how can it be at 25? If this is exothermic, doesn't it get warm? Are you guys familiar with this? I don't know if your Chem 1A covered this. So that's why I'm repeating this right now. All exothermic reactions, no matter how hot it gets, like if I combust methane, I start off with methane and oxygen at 25, and then the temperature skyrockets to 800 degrees C. Should I have the final temperature of the CO2 and water at 800 degrees C? No, the final temperature of the CO2 and water should be at, it turns back to 25. So what happened to all that heat? Yeah, the heat went into the surroundings. And so we always do chemical reactions starting at one temperature and ending at the same temperature. And any heat that's produced is going to be dissipated into the surroundings.
That's why it's exothermic.
That's why it's exothermic, exactly. And so, Well, let's just take a look at this. And so, what can we say about the kinetic energy? Kinetic energy, temperature is directly proportional to the average kinetic energy. Temperatures are the same, therefore the kinetic energies are the same. What can we say about the volume? Were any gases produced or consumed in this? No. Volume didn't change. And so the only change here was in terms of potential energy. It's chemical potential energy. This is what we call chemical potential energy.
Why does the potential energy change?
Hmm?
Why does the potential energy change?
Because the reactivity of copper 2 chloride and zinc is different than the reactivity of zinc chloride and copper.
Okay.
Let me give you another example of potential energy. If I had 1 pound of hydrogen and oxygen gas, and I asked you, can you transport this in your car over to? I have a friend that needs some hydrogen and oxygen gas. Versus if I had 1 pound of water, is there a difference? I mean, it's 1 pound of 1 pound, and usually shipping rates are based on how many pounds you carry, right?
Yeah.
And therefore, it's probably the same. 1 pound of hydrogen and oxygen versus 1 pound of water.
Yes, it's the same.
It's the same?
No, there's a lot more potential energy in the gases.
Right, there's a lot more potential energy in hydrogen and oxygen because it's an explosive mixture. You don't have to worry about water exploding, but you have to worry about hydrogen and oxygen exploding. That's chemical potential energy. But I might say, hey, wait, but they're both at 25 degrees C. I got water at 25 degrees C, I got hydrogen and oxygen at 25 degrees C. They have the same kinetic energy. They have the same kinetic energy, but their potential energy is different. So this is why potential energy changes, because this mixture has a different reactivity than this mixture. This mixture is a stable mixture. This is unstable mixture.
Wait, so potential energy depends on reactivity?
Yes, but it's more than that, because you got potential energy stored in the intermolecular forces. You got potential. Go back and read chapter 7 about potential energy. Why it's difficult to determine. That would probably be the most helpful rather than me repeating your stuff. Okay. And then just look and see. Well, potential energy is a form of what we say, a form of energy, and this potential energy can be converted, into, well, basically this is going to be energy that's going to be lost into the surroundings, right? Right. Going to be lost into the surroundings. Well, that energy can be lost into the surroundings in different ways. For example, we're doing electrochemistry today, and one way we could lose that energy into the surroundings is by this. This is redox reaction with electron transfer. So basically the copper 2 gained 2 electrons to form copper solid, and the zinc solid lost 2 electrons, Zn2+. So if there's a way that we, because the mechanism for this is the copper 2's got to collide with the zinc, right? Copper 2 collides with the zinc and then rips off the electrons off zinc, precipitates out copper metal, right? But if there's a way to force the copper to, to feed it through some kind of straw, rather than attacking the zinc directly, it has to suck the electrons off the zinc through a straw or some kind of conduit, like a copper wire,
Wow.
something like that. Then we can generate electricity, But how do you do that? Well, we're going to do that today. You'll see it's not that difficult. And so one thing we could do is we can convert this potential energy change, right, into electricity. And there's going to be electricity, which is work, in some heat. Because, when energy is exchanged with the surroundings, it can be exchanged in the form of work or heat. And so work would be generating voltage and pushing electrons through the straw, the circuit, or whatever, the wire, the conduit. And so these are the different types of energy we think about when we're thinking about entropy in terms of energy. You know, there are some forms of energy which have high entropy, and there's some forms of energy which have low entropy. You know, high entropy is disordered, and so what would be the most disordered form of energy that you can think of? Let's not talk about radioactive.
Electrolysis.
Just for the chemical reactions like this. Would it be electrical energy? You know, generating electrons through some kind of, having them go through some kind of conduit? Or would it be potential energy like this? Or would it be heat? What do you think would be the most disordered form of energy? Heat. Heat has a lower, not lower, has a higher entropy because it's more disordered. All you're doing is you're just dissipating kinetic energy into the surroundings, and it's just transferring kinetic energy through collisions. So that's not very ordered, right? And so that's what we call a higher entropy energy. Whereas something like this, chemical potential energy, this is much more ordered because we don't have to convert all this energy into heat. So for example, if I burn methane on a Bunsen burner, you know, that all goes to heat. A little bit of work because you hear sound and you see light, right? So a little bit of work, but mostly heat. But if I burn methane in a car, you know, one of those CNG, compressed natural gas vehicles, then a lot of that potential energy is converted into mechanical work, you know, driving the pistons and the tires of the car. And so I don't have to convert this all into heat, even though delta H people say that's a heat reaction. Well, yeah, but I can use this chemical potential energy to do work also, right? And you know, there's in physics they say have something like the Carnot cycle. It's hard to convert like this random energy like heat into work. You know, going from a disordered energy to an ordered energy is less efficient, right, than going from something that's like ordered to something that's disordered. You know, so they have something called the Carnot, but you know, we don't worry about that because we're starting off with a pretty highly ordered energy. And so this is why the second law of thermodynamics says what? The second law says that the entropy of the universe increases. Well, if we have a heat dump from our system, then what's going to happen to the entropy of the universe?
Increase.
Yeah, increase. Eventually this energy is going to be converted into heat. Eventually, right? Even if we do mechanical work or whatever, electrical work. And so so that means the entropy of the universe increases for exothermic processes, right? You see? Whereas the reverse, if we try to get heat, can I just cook this? If I'm going to heat this up, I'm going to just cook zinc chloride with copper metal. If I just cook that on a stovetop, is that going to revert back to, you think? No. So, you know, it's a... So, anyway, there's entropy in energy as well, and that's why when I say there's two driving forces, there's really only one driving force. One driving force is that the entropy of the universe increases, which is the second law of thermodynamics. But it's a lot easier to think in terms of energy. You know, minimize energy, maximize entropy. All right, so with that said, let's take a look. I just have this video, a short video. I'm going to show.
Videotape. John.
I didn't want to.
About.
John.
No, I'll be there. You guys know how to VCR?
Yes, of course we have VCR. We're low budget. I hope this. That would be nice because this VCR wasn't working last time. I tried it. So. Do you let's see if this is working first. We got audio but no video. That's a DVD.
That might be the button that switches it from DVD to VCR on the machine.
John, what's the purpose with the VCR?
It was the awesomest technology of the 80s.
What's the purpose of the VCR? Yeah, you just tell us how you do
The
it?
source picks it up.
Well, John, if you're, you know, technology from the 80s, you know the button?
Go for
Is
it,
this on
John.
the, leave it on that thing and then switch the button here.
All right.
It says it's on VCR.
I know, it says it's on VCR, but
Oh, even if it was on the DVD one, it wouldn't show?
It wouldn't show, but that's audio only, John.
No, that didn't do it. I wonder if it's like one of the buttons.
I should have checked it before. I thought it was fixed, but sorry.
Maybe there's a remote for it that
Yeah,
you can flip it over, but
forget it.
yeah.
All right.
So you could just act it out on.
No. All right, so the question comes about is, so I want to convert some of this chemical potential energy into electricity. How am I going to do that? And so that's what we're going to do today. We're going to play with batteries. And so let me set this up. Anyway, actually, let's finish this one. This is Chem 1A, but for Chem 1B, what are we after? We're not after delta H necessarily. We're after delta S and delta G, right? And so we want to know what delta G is for this. Delta G is what we call the free energy. The free energy is the total energy, including the entropy change. So delta G is going to equal delta H minus T delta F. And so this is what we're going to look for. In the free energy, they call it the free energy because this is going to be the freely usable energy. This is what we can use to convert into electricity. And so from now on, you're going to be looking for delta G's. But delta G, you know, we have these little zeros here, which mean standard conditions. And not only that, our delta G is limited to, right now it's limited to 298 Kelvin, right? I mean, we could change the temperature maybe, but what types of things impact delta G? The temperature for sure changes delta G. Did we do that calculation yesterday? And so you could actually make a spontaneous reaction go non-spontaneous, or vice
Yes.
versa, just by changing the temperature.
Oh, yeah.
I remember.
And also, the concentrations and pressures impact delta G. The same thing can happen. You can change the concentrations and make a spontaneous go non-spontaneous, and vice versa, just by changing the concentrations and or pressures. And so we can modify delta G, the driving force of the reaction, by manipulating the concentrations. And so let's take a look at this reaction here and see. Well, the first thing is we don't want the copper 2 to attack the zinc directly, so we have to separate them. And so we separate them into beakers, let's say, here. And so we'll put the copper 2 here. But if this is a piece of metal here, but we don't want this piece of metal to react with the copper 2. And so this should be an inert metal, or what else conducts electricity that's fairly inert? What else can... zinc is not inert. Zinc is very reactive. Uh-huh.
Platinum.
Well, platinum's a metal. Platinum is a pretty inert metal. Silicon doesn't conduct electricity very well. It's semiconductor, so its electrical conductivity is quite low. But something that has reasonably high electrical conductivity and is fairly unreactive is graphite. And so we use inert metal or graphite. And so the inert metal depends on what we have inside here. If we don't want it to react, then what are our choices? Well, if we have copper 2, can we use zinc here? No, we can't use zinc because that'll react directly. We need to use anything less reactive than copper. So copper would work because copper 2, if it attacks copper, then no big deal because we got the same thing, you know. Or what's less reactive than copper? Silver, gold, platinum. As you get more and more reactive species here, then we have to use more and more expensive metals. Eventually we have to use one of the most expensive metals, which would be platinum. Well, actually, we wouldn't want to use plutonium. Plutonium is actually a soft metal like lead. And it's not so hard to oxidize plutonium. But all you need is like a, you know, they say a dollar bill is like a gram, so you need about 1/1,000,000th of a dollar bill for a lethal dose of plutonium. Yeah, so if you cut up your dollar bill into a million pieces, then all you need is one of those.
Wow.
But it doesn't kill you immediately. You just end up having such a high probability of getting cancer that eventually you'll die. Well, so we don't want to use plutonium. So what should we do? There was an idea of getting rid of plutonium, radioactive waste, by shooting it out in space.
Terrible idea. If anything ever went wrong between here and space, we'd be in trouble.
Yeah, right. You just vaporize plutonium. I think it's a bad idea. You're right, especially some of those space missions.
Upper atmospheric winds.
Challenger
Challenge.
and all those probes, satellite. Well, anyway, so we need some kind of unreactive metal or graphite. Graphite's cheap. It's fairly unreactive. The nice thing about copper is this, because what happens is copper 2 is an oxidizer, right? And what do oxidizers want? This is chlorides in here, let's say. Copper 2 wants electrons, right? And so it's going to try to take electrons off this metal. And so there's going to be electrons here because metals have a sea of electrons. And if copper 2 is capable of taking 2 electrons, it's going to form copper solid. And that copper solid is going to deposit right on the electrode, so it's going to coat it or plate it. That's kind of hard to see. And so the advantage of using copper is that we coat copper metal with copper metal. You know, whereas if we use platinum, what we're going to do is we're going to coat platinum with a coating of copper metal if it takes the 2 electrons. Graphite, you know, graphite might be cool because graphite, you just take a piece of graphite and put a thin coating of copper on it, it'll look kind of nice, maybe. But you wouldn't want your gold or your platinum to have a thin coating of copper, would you? No.
What a waste.
What a waste, right? But is copper 2 capable of oxidizing any of these? No. And so it can't take the electrons. It's stuck, right? But what we take advantage of is this. You know, we'll just have this piece of metal in contact with zinc, a bar of zinc over here. And the thing is this, we got this sea of electrons, and so it's going to be like a train. And so the copper 2 is incapable of pulling the electrons off copper or any of these, but it's tugging on the electrons, and it's going to fill this tug all the way to this other piece of metal because of the electrical conductivity here. And then when we get to the zinc here, is copper 2 capable of oxidizing zinc? Yeah, totally capable of oxidizing zinc. In fact, the zinc will form Zn2+ and 2 electrons, and those 2 electrons can get fed into what we call the circuit over to copper 2, and this is how we generate electricity in a redox reaction. Right. But is Zn2+ stable in air? Can I just spit out Zn2+? No, because I can't just form cations without forming anions. So there's going to be an electrical neutrality problem here. There's also going to be an electrical neutrality problem here, because I can't consume my cations and just leave a beaker of anions, can I? And so this is called a space charge. The space charge is going to generate such a high voltage. A voltage is a separation of charge that, you know, it just can't sustain. There's going to be no electricity generated. So one way to help with this is Zn2+ is highly unstable in air. So if we can make it Zn2+ AQ, that's way better. Zn2+ AQ is going to help stabilize things because now we can have waters surrounding that zinc, right? And so air is not good. It's got to go into solution here. But we're going to run into the same problem. We're going to get a beaker of cations and we're going to get a beaker of anions. That's not good. That's not good, and it's going to immediately stop our electrons from flowing. And so we have to have some way of neutralizing that space charge. And so the one way that we have of neutralizing that space charge, well, there are multiple ways. But a common way of neutralizing that space charge is to put what's called a salt bridge between these two. Salt bridge. The salt bridge is going to be a salt solution or gel. Salt bridge is going to be what we're going to call inert, because it's not going to participate. It's going to be an inert solution or gel, or even solid. You know, they have actual solids that have like tunnels into them. The solids are like They have names for a class of them called zeolites. Geologists are totally into zeolites. But they have these tunnels or channels in which the ions can flow through a solid. And so, in fact, some of these are what they call super ionic conductors because they conduct electricity just as well as copper metal. But they're just ions flowing through channels in the crystal structure. So it doesn't have to be solution, gel, or gel. It could actually be a solid, solid ionic conductor. And so let's pick an inert salt like sodium chloride should do it. And so here I'll put in sodium ions and chloride ions, AQ. Eventually these are going to diffuse in here, but initially it should work. What's going to happen is this. As the Zn2 plus, for every Zn2 plus that's formed, 2 chlorides are going to be drawn to this beaker to neutralize that. And for every copper 2 plus that's consumed, I got to make up that charge. So 2 sodiums are going to be drawn to this beaker so that the chlorides charge balance and the zinc ions charge balance. And so the purpose of the salt bridge is just to maintain charge balance. All right, so what's going to happen is if I have a salt bridge in there, then that's going to help neutralize the space charge and allow the electrons to flow. The electrons are going to flow left to right here. And the ions flow here. And so there are actually what we call 2 circuits here. Circuits are just this flow of charge. The 2 circuits are, we have this one that's called the external circuit, which is the electrons flowing here. And then we have this internal circuit in which the ions flow here. All right. How strong is this flow? Well, the flow is going to depend on how strong of an oxidizer you have here. How strong is copper, how strongly is copper 2 pulling on the electrons over here? Is it pulling very strong? And then it's like a tug of war, how tightly is zinc holding on to the electrons here? When you balance those 2 things out, then we generate what's called a voltage. A voltage is essentially what you can think of a voltage is, there are two different ways you can think of voltage. Voltage is separation of charge, right? Positive charge over here, negative charge over here, you're going to generate a voltage. Another way of thinking about voltage is like pressure. It's the pressure on the electrons flowing through the wire here. And so this is like water pressure. If you have a garden hose and you want to feel the pressure of the water flowing through that, how can you feel it? Well, you just put your hand over and then feel how much pressure there is, right? Well, in order to feel the total amount of pressure, you have to block off the flow completely, right? And then you can feel how much pressure there is. Because if there's water leaking out, here, you aren't going to feel the full pressure. Okay? So in order to measure the pressure of the electrons, we insert a voltmeter in here. But what we have to do is we have to completely block off the flow. The voltmeter will block off the flow so that we can measure the total pressure on the electron. The pressure being the force on the electrons. And so if we stick a voltmeter in here, we're gonna shoot the needle out here. But it's not allowing any electrons to flow. It's just measuring, how much force there is on this. In order to get the reaction going, we have to remove the voltmeter and then let the electrons flow. And so we're interested in volts here, how many volts are we generating? And so the volts are going to depend on how strong of an oxidizer you have, how strong of a reducer you have, basically. Right? And so we're going to measure some voltages of various cells, and then we're also going to mess up the concentrations, I think we have 0.1 molar. 0.1 molar is not standard, but it's okay. We'll use 0.1 molar, 0.1 molar. and then we're going to mess with the concentrations. So for example, this is one way you can think of concentrations. You know, right now, which one's stronger, copper 2 or zinc 2 as an oxidizer? Copper 2, but that's under standard conditions. Standard thermodynamic conditions says that both of them are at one. Both of them are at 1 molar, right? What if I go totally non-standard? Okay, think about this. Now let's have 1,000,000 copper 2s versus 10 zinc 2s. What's going to happen? If I put 1,000,000 copper 2s over here versus 10 zinc 2s, and there's a tug of war, actually there's a tug of war for the electrons. You know, the zinc 2 is trying to pull the electrons off this now, generate some. And the copper 2 is trying to pull electrons off this. Under standard conditions is weird. You know, when you do things under standard thermodynamic conditions, if I did this under standard thermodynamic conditions, you know, what am I trying to make in this reaction? I'm trying to make zinc 2. But if I do this under standard thermodynamic conditions, I have to start with product. And so it's kind of funny because if you want to do this reaction under standard conditions, you have to mix the products and you have to mix the reactants together. Otherwise, how can you get 1 molar zinc 2, right? And so doing things under standard thermodynamic conditions doesn't make sense for a lot of reactions because you're trying to make product, right? But if we didn't have standard thermodynamic conditions, then the calculations would just be too horrendous. And so we'll sacrifice that so that we can figure out what's going on. So if I were to do this under standard thermodynamic conditions, then I'm going to have 1 molar Zn2 plus here, 1 molar copper 2 plus, and there's a competition between oxidizing agents. Which one's a stronger oxidizing agent? The copper 2 plus is stronger, and it's going to pull electrons this way, right? But what if I go totally non-standard? So for example, I don't want any zinc in here. If I didn't have any zinc in here, Zn2 plus, what do you think is going to happen to that voltage? It's going to go higher because, you know, Zn2 plus is not a good oxidizer, but still it's an oxidizer. It still wants to pull electrons, right? And even though it's weak and it's going to be totally overpowered by copper 2 plus, it's still trying to pull the electrons back. And so there's a little bit of tug of war, but it's a totally lopsided tug of war because copper 2 is going to win, right? And now if I even weaken this further, how can I weaken this further? By, just limiting or diluting it, or, you know, just like dilute it. And so now there's 10, let's say there's 10 zincs versus 1,000,000 copper 2s, then the voltage is going to even go higher, right? But now let's say this. Now I want to manipulate things a little bit. I'm going to put 1 billion Zn2 pluses here versus 10 copper 2 pluses. If I put 1 billion Zn2 pluses and only 10 copper 2 pluses, who do you think is going to win now? The zinc. And so if I did this, if I put 1 billion copper Zn2 pluses and just 10 copper, the voltage is going to go like this. And actually it's going to go backwards because now I've just changed delta G. You know, delta G's gone non-spontaneous or reverse reactions, now spontaneous. And so I can change, you know, delta G with concentrations and or pressures, you know, to make it do different things. And the concentration is just going non-standard here, you know. And so I just have a huge concentration of Zn2 plus. This is a tug of war. You know, you got a tug of war, you got 1 billion Zn2 pluses on one side and only 10 copper 2 pluses on the other side. And this is a lopsided tug of war. The Zn2 plus is going to win, right? And so all this stuff you've memorized from the chart is when it's a fair, even playing field, right? Once it becomes unfair, then we have to make adjustments. Well, how do we make adjustments? Well, we make those adjustments using the thermodynamics that we're going to do in chapter 19. You know, we talked about modifying the temperature. The next thing we're going to talk about is if we modify the concentrations, how does that change delta G? And so we're going to spend a lot of time looking at non-standard because standard conditions is pretty easy, the calculations. When we go non-standard, then it becomes more complicated. And we're going to go non-standard because, you know, how often are you going to do a reaction where you mix that like that? You know, it's rare. But it could happen, you know. It could happen that there's 1 molar, 1 molar. But as soon as, you know, as soon as this reaction goes, as soon as electrons, let's remove the voltmeter, as soon as electrons start flowing here, then the concentrations immediately change, and as the concentration immediately changes, delta G changes too. And so immediately as the electrons start flowing, this voltage actually goes down. Because there are going to be fewer copper 2 pluses and more Zn 2 pluses. Right? But there's easy ways to manipulate the concentrations for us. For example, one easy way to reduce the free copper 2 ion is to add concentrated ammonia. If we add concentrated ammonia to this beaker, actually you might not want to add concentrated ammonia because it smells. So you might add 6 molar ammonia or something. If we add ammonia to this beaker, the ammonia is going to complex with the copper 2, leaving the free copper 2 concentration very small. You know, how much free copper 2 is there in a 6 molar ammonia solution? Exceedingly small. And so just by adding ammonia here, we can tip the balance. I don't know if we can tip it enough, though, because our Zn 2 plus is only 0.1 molar. But we could try it. You know, we could try to defeat the copper 2 and make the electrons flow the opposite way. Watch the voltmeter. Right? So we'll play around with that. Or we could make the voltage go higher by trying to, you know, dilute this. You know, we're going to start off with zinc. Actually, we got to start off with zinc in this beaker because that's under standard conditions. We're going to start off with zinc sulfate, actually. This is going to be copper sulfate. Looks like. So we start off with zinc sulfate. Well, we could reduce that concentration by just diluting it, you know, dump some of the water out. The more dilute it is, the less impact it's going to have. And so all we're going to do is we're just going to play with batteries and then just try different things. You know, we could try different electrodes and different things to see how that impacts the voltage. And when we have a voltmeter here, like this, you know, and in a voltmeter here, you know, the red, well, we give names to these. So let me just tell you what the names are right now for the components of the battery. This is called an electrode here, and so this is also an electrode here, but these two electrodes are different because this electrode here is actually a reactant, zinc. The electrode is just like a conduit for electrons. You know, it just feeds electrons in or takes electrons out. And so we need some kind of electrical conductor to do that. The electrodes are going to be defined by what ions travel to that. So for example, cations go to this electrode, so we call this electrode the cathode. And then if we look over here, anions go to this electrode, so we call this electrode the anode over here. And then what we do is we generate electrons at the anode or at the cathode. Where are electrons generated? The electrons are generated here. So electrons are generated here.
Why doesn't it generate at the cathode?
Electrons are consumed at the cathode because electrons are generated here at the anode and then consumed at the cathode. Now, that means what occurs at the anode? Oxidation or reduction? What generates electrons? Oxidation or reduction? Oxidation. Oxidation occurs at the anode. Reduction occurs at the cathode. Right. And so at the anode, the reaction here is the Zn solid goes to Zn 2 plus 2 electrons. So I'll write that here. Zn solid goes to Zn 2 plus 2 electrons. These are the two half reactions. This is called an oxidation half reaction. This is a reduction half reaction. Now, one final thing, because you know these leads on the voltmeter are color coded, and so what do you think is the positive electrode? What do you think is the negative electrode? Yeah, the cathode is going to be the positive electrode here, and the anode is going to be the negative electrode, where we're generating electrons. You see that? Here. And so when we hook up our voltmeter, we want to put the red lead goes on the positive, right? And black lead goes on the negative. Otherwise the voltage is, I mean, you could do it the other way, but you know, it would be negative voltage rather than a positive voltage. It's not a big deal, but it's all right. Okay. I think that's all I wanted to say for this right now. And so we'll just use the rest of the time just to play around with the batteries. The salt bridge, the way we're going to make it is we're just going to use potassium chloride, put it in a petri dish, and then we have paper, strips of paper. You'll just dip the paper in here, saturate it, and then connect it. But what you want to do is this. You want to set up the battery like this. This is called a battery. You want to set up the battery like this without the salt bridge, and then measure the voltage. And then with the voltmeter there, you're going to get 0 volts. If there's no salt bridge there, you get 0 volts because space charge, right? Electrical neutrality. And then you take that salt bridge and you put it in there, and boom, immediately you see a voltage. It's kind of interesting. So why don't you try that? Or when you're measuring the voltage, remove the salt bridge. See what happens. All right, but anyway, I'll let you play around with it however you want. This is going to be an unstructured lab. Okay. Yeah, you just